lesson, I gave you the definition of the gravitational potential. Right, similar to potential energy, the only difference is the work done per unit mass. The only difference is this part, right? It's defined as work done per unit mass from infinity to that point. Okay. The graph looks like this. So usually we give small r as a general value and capital R as the fixed value. In this case, R being the value of the radius of the Earth. Right? That's where we left off last lesson. So, finally, right? So, here I want to introduce to you, I've introduced to you the idea of potential. Now I need to introduce to you the idea of equipotential lines. Remember, I said I want to tell you about that in this lecture previously. The circular lines that you have right on the page on fields, you saw these circular lines. These circular lines are what you call equipotential lines. Those of you who learn geography in secondary school, you know when you draw the relief of a mountain, the height is joined, the parts of the mountain that has the same height is joined by the same line, right? It's called a relief line. So it's the same idea. The equipotential line means that on that line, on that same line, the potential everywhere on that line is the same. Okay? But here I ask you a question. You have here two equipotential lines. Which one is of the larger value? Which one is of the larger value? The one closer in or the one further out? Which one has the larger value? Alright? So only 50-50. Anyhow, guess also can get correct, right? Okay, so show me your hands. Who says it is the one on the inside? Hands up, larger value. Hands high up and wave. Okay. Who says it's the one below? Further away is the higher value. Hands up and wave. One, two. That's why I get to keep my job. The answer is the outer one. The further away you are, the larger your value. Larger as in bigger. Not the magnitude. I'm talking about including the sign. Because gravitational potential has a negative sign. The further away you are, the less negative it is, because we take infinity to be 0, hence the larger the value. Correct? Can? Understand now? So if I ask again, which one has a larger value? Now you all know, it will be the one closer to the outside. Okay? So the red line will have the larger value, the orange one will have the slightly smaller value. And in this case, right, because it is governed by this equation, right, you can draw circles. Those with the same radius will have the same value of potential. Okay? Example 11. Right? If you look at the question, if you look at the graph, can you see that point P, the value on the left-hand axis reaches negative 1.3. And if you look at the scale, which is given below, it is actually the scale of potential. So this is a potential distance graph, a phi r graph. Potential is given, pronounced as phi, that circle with the line through it, right? This is pronounced as phi. So potential phi is negative 1.3 times 10 to the power of 6 joules per kg. Okay, that's the units for potential. The question is how in the world did you get this value? Right? In the true question, they did not ask this question. They just give you the answer. But we are learning. we ask ourselves, hey, how do you actually get this value? Actually, you can get this value. Okay, I'm going to show you. Potential is a scalar. Potential energy are both scalars. Remember, force and fields are vectors. Potential, so if you look at my summary page, those two on the bottom are scalars. You can add the values up directly. So the potential at P must have been due to the potential from Moon and the potential from Earth. Two of them add together, both of them are negative sign, right, to get this value. Okay? This is what you need to copy down. I need you to know this idea very well. Okay? So how do you get this graph? So if you have this, I can actually draw a potential graph due to Moon outwards like this, due to Earth also outwards like this, and add together to get this negative graph. To this, get this final graph here. All right? Let's simply add them together. Okay? Then we can finally attack the question as it was presented in a 10-year series. Right? A rock of 1 kg falls from point P to the surface of the Moon. What potential energy does it lose? So again, this is a potential graph. Potential is energy per kg. Right? Potential is energy per kg. Look at the units. It gives you a very strong hint. So if you lose, from here to here, you lose about 2.6. Not about, you lose exactly 2.6 worth of potential times 10 to the power 6. How much energy would you lose, right? So, answer? Right? The change in, so all the symbols are, let me read to you in real human language. These are all Greek, literally. You know, there's this expression, right, in English that this sounds like Greek to me, right? Literally, right, this is Greek. Delta U equals to M phi P minus M phi M. Right? Okay. So this is delta is also a Greek letter, phi is also a Greek letter, but okay, it's fine. So let me explain to you in human terms. The change in energy is the mass times the potential minus the mass times the potential at M. So M at P minus M phi at P minus M phi at M. You can take the mass out as a common factor, which is 1. The potential at P is negative 1.3 times 10 to the power 6. The potential at M is negative 3.9 times 10 to the power 6. Bring them together, you get a loss in 2.6 times 10 to the power 6 joules. That is 2.6 million joules. It's a lot of energy loss. Okay. Right? Next, they ask you what is the speed of impact. So it lost this amount of gravitational potential energy, assuming no other dissipative loss of energy, all of that GP becomes K, right? All of that GP becomes K. So it's just GP equals to half mv squared. You have something approaching to you at 2.28 kilometers per second. It's pretty fast. You try not to get hit by that rock, okay? Next, if the rock were to fall from P, however, to the surface of the Earth instead, what would be the speed of impact? What do you think? If it's to fall to the surface of Earth instead. So you look at the graph, right? If you fall from P to the moon, you lose only this amount of potential. You fall from P to Earth, wow, you lose so much potential, right? So you multiply it by the mass, you should lose a lot more potential energy, right? So same thing, right? You take the initial initial potential minus the final potential on Earth, right? Get this velocity. Is it correct? Wait. Oh, yeah. So which one is faster? The one falling to moon or the one falling to Earth? Earth, right? To moon is 2 point something kilometer per second. This is 11 kilometers per second, higher. Right, higher. Do you remember what's the escape speed from Earth we got before? 11.2. Is this close to the escape speed from Earth? It's quite close already. Also, somewhere in between moon and Earth, you already get somewhere close to your escape speed. Which shouldn't be a surprise because as you go further away, the increase in potential energy is actually very small. Right. Sorry? So we have a question here, very good, very good. I love questions in lectures, especially this lecture. Because I'm pretty sure not all of you got it, right? So questions are amazing, right? You look at this, this is the what graph? It's a potential distance graph. Right? The question was, how do you decide which is the direction of force, correct? How do you decide? If you are at P, incidentally, if you are exactly at P, you will stay there. Because that happens also to be the point, right, where the field is 0. There is equal pull from moon and from Earth. Why? Because the gradient is flat. We're going to see that in part 7, right? Page 17 of the notes later on. Right? We'll see that later on. So any point to the left of moon, you'll feel a force towards the moon. Any to the point to the right of P, you'll feel a force towards Earth. So how do you imagine this? So every time I teach this, a simple way to imagine potential is imagining it as to be a mountain. This curve you have is actually the shape of a mountain. If you put a rock to the left, you'll roll to the left. You put a rock to the right, you'll roll to the right. Essentially, that's how I see it. Okay? Of course, I see it with a bit more equations, but if I simplify, that's what I see. Okay. Right. Also, they say if there's atmospheric friction, the speed will of course be less than that, right? Because some of it is converted to work done against friction. Okay, that's it. Okay, don't need to write all the words. Don't use my words, use your own, right? Practice your own words, which is a lot easier, right? Moving on, 5.2. Alternative convention for potential energy at points close to Earth. Right, we always choose potential energy on the surface of Earth to be 0 in secondary school, in the topic of world energy power, so on and so forth. Right? So if we use this as a reference, right, we can write this. Okay? But this is actually not very common now. It's really, really not common. Because for all users of gravitation in G is not constant, right? So you usually cannot write this. Right, so this is just one of the simple representations. I'm not going to belabor the point. Now let's talk about energy of satellites. Remember, we started off in episode 1, first lecture, right, of satellites in orbits. Okay, now we can finally talk about the energy of satellites. After knowing the potential and potential energy, let's talk about the energy of satellites in orbits. And here I want to make a few differences. Let's say my head is Earth, again. I place a rock here. Where will it go? Where will it go? It will go towards me, right? Okay. Something that's orbiting, something that's orbiting is different from something that's at that point at rest. Can you differentiate the two? You have to differentiate the two. Because the energies are vastly different. How you consider the energies are vastly different. Something that's orbiting, the energies are considered in a very different way than something that you drop from that point and falls towards you. Okay? Why does something stay in orbit? It's because it has a kinetic energy to move it around in a circle, despite having a force pulling towards the center. Okay, so with that, let's start. The total energy of a satellite can be given by total energy being K plus U, K being kinetic energy, U being potential. This is the mechanical energy of a satellite, right? In World Energy Power, a very good lecturer told you that. Kinetic energy is half mv squared. Potential energy is negative gmm over r. Correct? This is the boring part. The powerful part is going to come next. So this as an equation is super not useful, right? Because there's so many variables and it's two parts of the equation. You know physics, we like it to be beautiful. So we consider the forces, right? Centripetal force and gravitational force. Gravitational force provides for the centripetal force. This is the 7th or 6th time that I'm actually saying this in the whole lecture series. Right? So you must know this. Right? Gravitational force on the left-hand side provides for the centripetal force. Here, we use mv squared over r instead of mr omega squared. Why do we choose this? Because we want to simplify away this part of the equation. Right? So we rearrange such that we get mv squared equals to this. Now we sub what we have here into this, and you get something amazing. You see that the kinetic energy, is exactly, not kidding you, exactly half of the magnitude of the gravitational potential energy. Right? Gravitational potential is gmm over r. Ke is gmm over 2r, which is interesting. Why? Because this means that the total energy is just half of the gravitational potential energy at negative gmm over 2r. Show you that. Okay. I take Ke, which is half of the magnitude of Pe. Put together, I get this. Okay? Digest, must digest it down. This means that for all satellites that are in orbit, this relationship will hold true. This relationship will hold true for all orbits. This means that if I have an object at radius 1 unit r, and an object at radius 2 units of r, the total energy will just vary by 2 times. And all the other energies will also have the same relationship. Okay? Which then allows us to plot this very interesting graph. This is your initial gravitational potential energy graph, given by this equation U. We found that K is half of the magnitude of GPE. So notice, when I plot it, you must be very careful. This height of this dotted line is about half of this dotted line. This one is about half of this height. right, from the axis. We also found that total energy is just half of the total of the potential energy. The total energy is half of the potential energy, which means it's slightly closer to the axis. So K and E are just mirror images of each other. U is a magnification downwards. Okay, this is how I want you to remember it. Okay. Time flies, man. Okay, well, you are busy drawing and copying in the equations. Actually, the equations you don't have to draw it because they are all already above the page. It's just that if you write it out, of course, it looks neater. Once you're done, please lend me your ears. Now you look at where my cursor is here. I know the line very straight. Okay, if you are at this point, where my cursor is. Oh, wait, have you heard of satellites falling back to Earth? Have you heard of that? Satellites that were previously in orbit, due to lack of maintenance, falls back to Earth? If you have don't, then this is the first time you hear it, and it's a fact. Okay? So what happens is this. You are initially at this radius, you fall back to almost hitting Earth, maybe at this radius. What happens to the total energy? It increase or decrease? It 1, 2, 3. 1, 2, 3. It decreases. Why does the total energy decreases? Maybe due to some kind of resistance. Maybe in the outer atmosphere there's still some air particles, so it collect. Then it lose energy. Okay? So it lose total energy. Does it lose potential energy also? But does it speed up? It actually speeds up. Right? A lot of my students say, oh, it's in outer space, outer space is moving, but it lost energy, so KE decrease. Then I feel shocked. Cannot. So you lose total energy. But because you lost even more GPE, you must have increased KE. Okay, you must have increased KE. Right? And when the satellite loses energy, it doesn't just, the satellite is doing this, doing in circle. It doesn't just lose energy, boom, go straight. It will spiral inwards. So it's a slow spiral inwards, gradually losing height. Okay, moving on. This is what I promised you. You look at your notes, there's only 2 pages left. Then I'm thinking at the time, wow, half an hour, how is Mr. Ho going to fill up the time? Is he going to tell us a story? No. I'm going to show you the power pack of this lecture, which I'm going to add value to. This is this. In work energy power, this was introduced to you. How I know? Because I gave that lecture. Right? The force, the gravitational force is related to the negative of the potential energy gradient. F equals negative du dr. I said that this is a common equation to be used throughout many topics, very gravitation, electric field. So this is a very important idea to comprehend. Okay, so I'm going to give you some examples later. And you also realize that G is related to the given, the gradient field G is related and given by the negative of the potential gradient. So I'm going to convert all this into more concrete ideas with my illustration later on. Okay? And I summarize the whole chapter with that picture on the at the bottom of that page. Okay? Copy finished? So what does these words mean? I'm going to show it to you. Okay, and this is a summary page. I'm going to help you overcome the difficulty of gravitation. Right? Many students say, wow, gravitation, I got 4 equations, remember? What gravitational force, gravitational field, gravitational potential, energy. Oh my God! As a student, I was also like that. So I know your pain. So I'm going to help you. Okay? Look at how I've organized these square boxes. Everything above has R squared. Everything below has R. Agree? Everything to the left has two masses. Everything to the right has one mass. So now all you have to do is to remember force is top left, field is top right, potential energy is bottom left, potential is bottom right. Done. Correct or not? Then you know it's R squared on top, R below, M to the left, M to the right. Then you can fill out all your. You have remember essentially just by running this method, you have remembered all four equations. Okay. More illustration. Everything above are vectors. That means if you add forces, I want you to have a red flag. If you say add these two forces together, oh, it's a vector. You must remember it's a vector. Add these two fields together, it's a vector. You must use vector addition, which is one of the examples I gave earlier. Example number 6. Okay, vector addition, example number 6. Scalar addition, example number 11. Okay. Now I'm going to go into the nitty-gritty, I think. This I already showed you before. Okay, let me just show you, since if you missed the animation, I have time to do it. I'll show you. Right, next. So you all know what is scalar addition, right? Scalar addition just add together. Vector addition, you must take care of the direction. This is a cool idea, right? Force. So sometimes you just say, wow, I don't remember. But hey, look, the left-hand side is just the right-hand side multiplied by m. So I told you, right, this is given to you, right, as an equation. Correct? Gm over r is given to you in the formula sheet. So to remember potential energy, just multiply by m, there, done. And you remember force, Gmm over r squared, so nice too. It's like a rhyme, Gmm over r squared, Gmm over r squared, right? You do that a few times, you divide by m, you get field. So easy. So simple. Right? I'm giving you the tricks to this. Really, this page took 7 years to materialize. Okay, took 7 years. So it's a crystallization of how to learn it easiest. Now let's look at this. What happened? Why is there it appeared too early? I must change the animation later. Now I want you to understand this. Remember, on the top of this page, I show you F equals negative du dr. What does it really mean? It says that force is the gradient of the energy distance graph. What it means is that the gradient on the UR graph is a value, it's a negative value of the force. Yeah. Sorry, of the force. Sorry, my friends. Okay. It's a negative value of the force. So, if your UR gradient is like this for a certain point, it will correspond. So the gradient here looks positive. You multiply by a negative value, you get a negative force. Make sense? Right? So Gm over r squared is here. U is here. This is what it means. Can? And now I'm super illustrating this all to you. Your seniors don't have this. Can? So if you're missing it, so yeah, the blinky yellow arrow, the value of the force is the value of the gradient here times the negative sign. Next, this equation again. If you are now given an area under the force distance graph, the area here, it is actually the change, right? So if you look at this line and down, you have this potential energy. The area here is the difference between the height of these two arrows. So if you move from left to right, you increase the potential energy. If you move from right to left, you are decreasing the potential energy. Okay? This is how you use this equation. You can use it to look at the gradient of the energy distance graph to find the value of force, or you can find the area and the force distance graph to find the change in energy. And it should not be scary to you because you have learned in work energy power, right? Some lecturer told you that before, that the area under the force distance graph is energy, correct? And the change in the area within 2 points is a change in energy. I've already mentioned that before. Okay. Next. Do we have time? Oh, Running out. Next. Right hand side. I repeat the same thing. Illustrate. I'm not scared, because I want you to get it right. If you have the gradient, right? If you have a 5R graph, a potential distance graph, which is your example 11 just now, the gradient of that is the value of the gravitational field. Right? So the gradient of it at a certain point is the negative value of the gravitational field. So the negative value of the gradient is the value of G. Okay? That's what it means. So if you look at example number 11 or number 12, you look at the gradient. At P, the gradient is 0, hence the field strength is 0, hence the force is 0. Okay? Closer to Earth, the gradient is steeper, the bigger the value of the force. Right? The bigger the magnitude of the value of the force. Okay? And also, with this, you can also interpret it like that. As the area under the GR graph will lead to a change in potential. Oh, the graph is not appearing. But oh, fine, whatever. Right, you get the point. Here, this change, if I move from left to right, I'm increasing the potential. Okay. Any questions at this point? So this summary page is very power packed. Right? If you understand it completely, it will help you to tackle all questions. Right? All questions within gravitation itself. It does not help you with the question that tackles across other topics, but that's not too difficult. Just apply the force, right? Like circular motion, so on and so forth. Moving on, example 12. It's all given to you. Oh, we may be able to end early today. Maybe I can start with a tutorial. Okay, wait, if I release you all early, which means you all must go and do your tutorial, right? You promise me, right? Right? Yes, you are nice people. I can feel it. You are just like me when I was young. Earnest and honest. Right. Instead, I explain the direction of resultant gravitational force placed on the position to the left and right of P. So this is the potential graph. You cannot tell the direction of field or the force. But if you look at what I've given you, right, to the left of P, the potential gradient is positive. Hence, the gravitational field is negative, right? Because G equals negative d phi dr. Means it's moving to the left because we take rightwards as positive. Correct? We take rightwards as positive. If the field is negative, it means it must point to the left. This is what this whole bunch means. On the right, to the right of P, If you repeat the reasoning, the gradient is negative. The value of g is negative d phi dr is hence a positive number. Hence, it must point towards the right and hence points towards up. Okay? So, if you don't like all this kind of tough reasoning, just remember what I said. Remember it as a hill. Where you roll the ball, you will decide where it wants to go. Right. This is an extra example which says a rocket starts vertically with our speed of v naught, after which engines are switched off. Show that at a certain speed at a height h is given by that monstrous equation. How do you actually do that in exam? Usually you try not to do this kind of questions, but if you do, you will attempt it like this. Right? The physics is again very, very, very easy. Right? The physics is actually this. The loss in KE is the gain in GP. You start out with half mv naught squared. The final velocity is v squared. Right? The gain in GPE, you take the GP that you have minus the initial GP, which is a negative value. Then you work out the math, blah, 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 and you get hit and you get this. Right? So the physics is really easy. The math looks intimidating, but it's actually also not too hard. Okay? It is just calculation-wise difficult. And that's it. And that's it. Right? So go back, and I stare at this picture. Ladies and gentlemen, go back and practice copying this out on your own 3 times a day. That's it. Goodbye. Have an early lunch. Any questions, come to the front. Thank you.